Hi everybody, this is Cal with a guide for sections 2.1 and 2.2. A note before I start, and I will have said this elsewhere, but you will want to have read Appendix A before going into this section, especially if you've never had exposure to basic proof techniques before, which is going to be for most of you. So make sure you give Appendix A a good read. So let's get into Chapter 2 here, and in Chapter 2 we're going to develop properties of the real numbers, R. And what I want you to pay attention to is the level of detail that the book goes into on proofs. You really need to be doing as much detail, if not more so, than the book is doing when you're starting out with proofs. And we'll let up that restriction later on to a certain extent, but you really do need to be thinking on a level where you're justifying every single thing that you're saying. So let's get into it. Section 2.1 is called the algebraic and order properties of R, and in this section we're going to be developing basically the algebra of the real numbers. We start from a set of axioms called the field axioms. A field is a certain sort of object. If you ever take abstract algebra, you'll learn about it. There are other fields besides R, but R is going to be the one that we're studying here. So we start with this set of 9 axioms, and our game is going to be that we are going to prove all of the algebra of the real numbers using just these 9 axioms. These are our only tools. So 2.1.1 lays them out, and we start proving things with them below. So take a look at Theorem 2.1.2. This has some familiar facts about the real numbers. Part A says that there is only one element that adds to others like 0. B says there is only one element in the real numbers that multiplies with others like 1. And C says that multiplying anything by 0 gives you 0, which is something you know. Take a look at the proofs here. It really has, for every single equal sign in here, it justifies it somehow. And you want to look at how it does that. I would actually say the book is not being as explicit as it could be. Honestly, I would probably just write out the name of the axiom I'm using above each equal sign here. Also, it has a neat technique here. If you look at Part A, it has z equals z plus 0, which is axiom 3. And then it actually turns that 0 into an a plus negative a, and so using axiom 4 for that. But think of it as adding and subtracting something convenient, and then it's rearranging the parentheses afterwards. And adding and subtracting something convenient, or multiplying and dividing something convenient, is going to be a really common tool for us. So pay attention to how they use it here in A and in B. But anyway, work through these proofs pretty carefully and make sure you understand how every equal sign is being justified. This is something that you need to be able to do as well. Theorem 2.1.3 are a couple more factoids that you're familiar with about the real numbers. Make sure you read that carefully as well. Below that, we talk about how we define subtraction and division. Again, things that you're used to, but we do need to define them. We're working from first principles here. And then we talk about rational and irrational numbers. The blurb down here is important to read. It gives you some good background. Your book says that the discovery of irrational numbers had a profound impact on the development of Greek mathematics. Profound is not quite the right word. People died over this. This is really big back in the day. And it presents, Baby's first irrational number in Theorem 2.1.4, the existence of the square root of 2, the fact that the square root of 2 is not rational. This is a great proof. It's a proof by contradiction. Again, if you're not up on that, read Appendix A. And this is a proof that you should be able to do. You should be able to recreate this proof for numbers like 3 and 5 and understand why it works. So spend a little bit of thought on that. Make sure that you understand what this proof is doing. It's a pretty cool proof. Then we get into the order properties of R. Again, this is really cool stuff. We start just by defining a subset of R that we're going to call P. It's the positive numbers. And we set out a couple basic properties of the positive numbers that should be self-evident. But from these inauspicious beginnings, we're going to get a whole lot of mileage. Just from knowing there's a thing called positive numbers and knowing how they work, we can get ideas of inequalities. So we define inequalities in 216 at the bottom of the page. And then we can use inequalities to derive all the rules of inequalities that we're used to. And I will say, you need to know these rules in Theorem 217. And I, again, read the proofs. Make sure that proving these things is something that you would be able to do. 217C in particular is something that we are going to use all the time. Make sure you understand what it's saying. It's something that you know, but you probably have not seen it expressed this way before. Theorem 218 gives us a couple more useful properties about order in the real numbers. Again, make sure you understand what these are saying, read the proofs. And I'm sorry, at the bottom of the page, we say that no smallest positive real number can exist. You should understand why. Now, Theorem 219 is extraordinarily important. This is going to be one of our basic tools. We're going to use this all the time to prove that a number is zero and other related things. Make sure you understand what Theorem 219 is saying and how it is proved. Theorem 2110 is, again, pretty important. You've used it many, many times in your life. And the corollary is important too. So those are cool. Below that, the rest of the section, I believe, is examples, but they're reasonably important examples. Read through 2112 and make sure you know how it's doing everything there. 2113 is some more, let's say, top-level examples. Interesting theorems that you can prove about inequalities and so on. They're interesting. I don't know that they're things that you need to like have memorized or whatever, but these are things that can come up occasionally, especially the first one. Actually, the first one we're going to use a lot. 2 and 3, they'll come up, but not so much. And C over here, Bernoulli's inequality, is really cool. It's a great proof with mathematical induction. It's, you know, make sure you understand this proof and how it's working. And I'm not going to say you need to memorize Bernoulli's inequality, but it's something that will come up from time to time. And that covers 2.1. 2.2 we'll cover really quickly here. It gets into absolute value in the way that the real number line works. Make sure, absolutely sure that you know definition 221. We will use that constantly. And Theorem 222 is pretty important. Most of the things in there are pretty obvious. I want to draw your attention to 222C, which we'll use quite a bit whenever we want to split up an absolute value inequality. D is pretty self-evident, I think, but we're going to use it to prove the next theorem in a moment. And do read over the proofs of 222. 223, the triangle inequality, is again basic. Use it all the time and make sure that you know it. And make sure you understand the proof. It's not difficult, and you should understand where that's coming from. We'll use the triangle inequality all the time, and its corollaries at the bottom of the page will come up as well. Make sure you understand the proofs there. 225 is an extension of the triangle inequality. I would say you should try to prove this on your own. It's an application of mathematical induction, and you should work out the details there. 226 gives examples of how some of these absolute value notions and inequalities are used. And then at the bottom of page 34 we get into the idea of the real number line. You've used this for years in other math classes. We have a notion of distance between 2 points on the real line. And then we talk about neighborhoods, and this is, again, a really important definition. This is basic to other things that we'll be doing. Um, Make sure you understand what an epsilon neighborhood is, what the picture is. And Theorem 228 it's Theorem 219, but in neighborhood language. Make sure you understand what I mean by that. And 229 gives an example or two. And I think that ties up the sections.